why don't you just take it away home?
Okay, good. You can hear me well?
Perfectly. Thank you.
Okay. Okay, great. Okay, yeah. So thanks for the invitation to talk. So I'll be talking about some recent work with say my student Sam Lusather, and which appeared in 2 papers recently. So one is a short paper, and the other is a much longer version. So yeah, of course, whenever we talk about quantum gravity, the first issue arises is the so-called problem of time. In quantum mechanics, time is an absolute concept. Say, yeah, you have to talk about evolution, and then you need time. But in quantum gravity, most of the time is actually meaningless, as it can be changed by arbitrary gauge diffeomorphism transformations. Okay. So this raises a sharp, in a sense, contradiction between the when you try to combine them together. So when I say most of the time, because there is one situation, so in anti-de Sitter space-time, actually the situation is much better, because there is an absolute asymptotic time. Because when you go to asymptotic infinities, a gauge transformation, by definition, they go to 0 there. So your time is no longer reparameterized at infinity. And then the time there is absolute. And so of course, this fact underlies the success of ADS-CFT duality. And also, this is also the reason why quantum gravity in space-times of other asymptotics, say asymptotic Minkowski or de Sitter, they appear much more difficult. Okay, because we don't now have a time. So, but in ADS, we can actually ask questions a little bit further. So even in the context, say, of holographic ADS-CFT duality, can we extend this absolute asymptotic time to the interior? Because we do want to understand the interior of the space-time and the physics there. Okay. So in the special class of states, say, which is static, which you have a time like Killing vector, global time like Killing vector, and the answer is trivially yes, because in that case, actually there is a distinguished slicing of your space-time. And yeah, in this way, you can actually extend the time meaningfully into the interior. But if you have a general time-dependent space-time, and then the situation is far from being clear.
Yeah.
And
yeah.
So yeah.
Do you need to tell me something? Now's a good time.
Yeah.
Somebody needs to mute.
Albion, you need to mute yourself.
Oh, sorry about that. Thanks. Yeah, I thought I checked my.
So an intermediate example is the internal black hole in ADS. Okay, so this is a well-known example. Say its duality is known from early days of ADS, from the ADS-CFT. Say the physics in the internal black hole geometry in ADS is believed to be dual to 2 copies of CFTs, CFT left and CFT right, in the entangled thermal field double states. Okay, and there are many things known about this duality, and many consistency checks, etc. Okay, and so one interesting feature about this geometry is that there is a time like Killing vector outside the horizon. And then using our standard ADS-CFT framework, then it's relatively easy to use the boundary theory to describe the physics outside the horizon. Yeah, it's just because we can actually now extend this notion of the boundary time to describe the interior physics. Okay, but this geometry is interesting. It's because it has a horizon. This time is not global. Okay, so the time stops at this horizon. Okay, And then that raised lots of mysteries. Say, for example, how do we use the boundary theory? How do we use CFT to describe the regions inside the horizon? Say this future and the past region. Okay, we'll use this label all the time. The right and the left region and the future and the past region. Okay, so the right and the left region can more or less be straightforwardly understood, but the future and the past region are rather mysterious. Okay. And also, how do we see a Kruskal-like time? So this spatial time can be naturally understood from the boundary theory. But how about the Kruskal-like time? Okay. And also, how do we see the horizons and the associated causal structure directly from the boundary theory? So, and in particular, even though these two CFT are not interacting with each other, and we do from the causal structure of the black hole geometry, the observers can actually fall into the black hole and they actually interact in the interior region. Okay, so there's all these mysteries due to that in this geometry, there's not a global time-lag killing factor. Okay, vector. Okay, so this is an excellent intermediate example for us to understand, say, emergent time, say, in the interior of the space-time. Okay. And so first, let me just quickly remind you how the standard notion of time, which we use to describe the black hole physics here. So the first notion of time is just the boundary time, and in the box corresponding to the spatial time. And from the evolution of the boundary theory, that's corresponding to evolve the system using the right Hamiltonian, the h right left minus HL, and that corresponding to you change the time slice in the box according to the arrow as follows. So for this evolution, you always stay outside the horizon. Okay. And the next evolution you can imagine is you consider HR plus HL, and again. And if you do such evolution on the, say, on some local operators, say in the box, you never take those operators inside, right? It will evolve like shown in this arrow here. Okay. But if you want to understand in this third figure, if you want to understand the time evolution to allow the Cauchy slice, which actually cross the horizon. Okay. And then you actually likely require some emergent time, okay? Because we don't have readily used boundary time to do it, okay? And so the goals for this talk is to tell you a construction, so the boundary constructions of this kind of Kruskal-like evolutions, okay? So this last figure is a Kruskal-like evolution, so that you can actually evolve. In the sense like the parallel to your original slice. And the second is that we would like to understand how the horizon and associated causal structure arise in the boundary theory. Okay. And so here is the my plan for this talk. So first, I will outline the main results. And then I will talk about the main technique we will use to actually achieve those results. And this is so I will review briefly entanglement structure in relativistic quantum field theory. And in particular, the important role played by type 3-1 Modular algebra there. So this type 3-1 Modular algebra actually brings additional structure. It's called the half-sided modular inclusions and translations. And that can be used actually to generate this emergent time, which can take us behind the horizon and generate Kruskal kind of time. And then I will describe, say, how do we construct, say, Kruskal-like time evolution from the boundary theory. And then I will end with some discussions. Okay. So before I continue, do you have some questions? Okay, good. Okay, so first let me just outline the main results. So what I will show is that there exists an evolution operator on the boundary. There exists, say, a class of evolution operators on the boundary, which have the which can be written, say, as explanation. Say this US is some unitary operator, and the G is some Hermitian operator, and this S can be considered as some kind of emergent time. Okay. So this G, which generates this emergent evolution, have the following properties. First,
Hong, I think Vijay has a question.
Okay. Yeah.
Hong, I'm afraid I have to ask, what is a type 3-1 algebra? I should know these things, but I don't.
Yeah, I will say a little bit more later. At the moment, it doesn't matter.
Okay.
Yeah, at the moment, it doesn't matter. It will come. I will not have time to give precise mathematical definition, but you will see physical consequences of it in the explicit physical example. Then I think that will give you some intuition. Good. Okay. So this G, so this generator of this emergent time, first it's involved both R and L degrees freedom in a non-trivial way. It's just not, say, a direct sum, say, of the Hamiltonians of the left and the right. Okay, so it's actually it's a more complicated involvement of the R and L degrees freedom. And the second, which is the most important property which makes this S to be a time, is that this G, the spectrum G, is bounded from below. Okay, so normally, say, when we talk about time, say, what do we mean by time? Okay, so in quantum mechanics, the only way, of course, there's many things you can associate with time, but in quantum mechanics, normally we distinguish time with space from the spectrum of their generators. Say, for the momentum which generate the translation of space, the spectrum is unbounded from both sides. But if you have a Hamiltonian, then the Hamiltonian is required. For sensible physical systems, the Hamiltonian is required to be bounded from below. Okay. So here, this G have this important property, and that's why we call this S an emergent time. Okay. And the third, and now if you take, say, a Bach operator in the right region of the black hole geometry, which I said we can easily treat using the standard ADS-CFT say dictionary, and then I can act this evolution operator, which is intrinsically constructed from the boundary, on such a Bach operator, say, in the R region. And then I will show it actually can take it inside the horizon for some sufficiently large S. Okay, and in particular, and so this gives you some kind of Bach evolution of some kind of infalling evolution of a Bach operator. And in particular, this evolution shows sharp signatures of the horizon, and it can be seen to generate this future and the past regions of the black hole from this right and L regions. Okay, so let me elaborate on this last sentence. What do we mean by sharp signatures of the horizon? Okay, so this S then qualifies as an infalling time. Okay, okay, so actually, in the example of the BTZ, which is sufficiently simple, we can actually construct examples of such US very explicitly. Okay, so now let me give you one such example. Okay, so again, this is the equation which will involve this operator, some Bach operator in the right region, using this evolution operator. And then you can show they exist. So at the beginning, because this operator, at S equal to 0, because this operator is in the right region, okay? And so by definition, it only involves the degrees freedom of the CFT right? Only contain the degrees freedom of the right CFT, okay? And now when you do this evolution, and now you can show there's a sharp S0 greater than 0, such that when S smaller than S0, this evolved operator still contained in the right CFT. But when S greater than S0, now it actually starts involve the degrees freedom also in the left CFT. Okay. So indeed, this is what we expect when you have an operator which crosses the horizon. So when your operator is in the right region, and then it can be expressed in terms of the degree of freedom in the CFT, right? But if this operator falls through the horizon, and once it crosses the horizon, and then it can be causally connected with the left region, and now it must involve the left degree of freedom. Okay, and so this is in some sense what we expect, even though for the for something to fall through the horizon.
Okay. Well, I think Matt has a question.
Okay.
Hi, Hong. I mean, maybe you're going to address this later, so that's fine. But I'm just curious at this stage if what you're saying is really involves gravity, or could I have made the same statements for a field theory, and I have two complementary Rindler wedges in field theory, and then I have, I propagate an observable across the Rindler horizon, and it's just quantum field theory, no gravity. Is that
good? Yeah, this is a excellent question. I will discuss this later.
Okay.
And that's a very important example to compare. Indeed, I will discuss that later. And also, related to your question, indeed, this concept is very general. We don't have to talk about black hole. We can also just take two quantum systems, say identical quantum systems, just entangle them. Okay, can construct some field double states. And then if such a US and S0 exists, then we may say, actually, this system have an emergent horizon, and they are some sense causally connectable. Okay, even though this is two distinct separate systems.
Oh,
for example, this kind of thing may be used to say to simulate, say, gravity. To simulate gravity and the signature of the horizon, say in the lab or something like that.
But you're saying there are quantum systems for which such a U of S and S naught don't exist?
Yeah, I would say for general systems, you will see later. For general systems, such a U and S don't exist, and but they can exist in some kind of larger limit. Say, for example, in SYK. I believe it can exist when you take the n go to infinity in SYK. So in the lab, if you can simulate in SYK, and then of course in the lab we cannot take n go to infinity, but just like you see a phase transition, you can see some kind of sharp signature, say some kind of horizon. Yeah, just like you see in the phase transition. Yes, Veronica. Yeah.
Matt, did you want to ask some more?
No, thanks.
I have a slightly different question then. In the gravitational context with the black hole, do you expect an upper bound on S, much larger than S naught, I guess, but that mimics the evolution, the slices hitting singularity, or does
good. Yeah, that's also an excellent question. Indeed, we will see an upper bound, and but has took us very long time, half a year actually delayed this paper. We tried to associate this kind of upper bound with the singularity, but somehow we could not find, at least within our current, I think it should be possible, but within our current calculation, we didn't see a sharp signature of the singularity, but I believe it should be there. Yeah.
Thank you.
Good. Okay. So now let me elaborate a little bit about this value S0. Okay. So now let me just draw the Kruskal diagram. So let's forget about the boundary. Just draw the Kruskal diagram for a black hole. This is the standard the Kruskal U coordinate and standard Kruskal V coordinates. And now suppose this is initial point X is in the right region with initial coordinate U0 and V0. And now if we evolve such an operator at such point, and then you find that this S0 is precisely equal to the log distance for this point to reach the horizon. So equal to minus U0. Okay, so if you along the U axis to fall through the horizon, and that so S0 is precisely given by that value. Okay. And in particular, if this point is near the horizon, and you can actually, you find this transformation is actually a local transformation. It is just the Kruskal law translation along the u-axis. Okay. But if it's not close to the horizon, so this transformation is actually non-local. Okay, but the non-local in a way respects the local structure. Yeah, causal structure. For example, it takes S0 for it to cross the horizon. Okay. So now let me elaborate a little bit further this causal structure generated by horizon. So we can consider more sophisticated quantity. So suppose we look at the operator in the right region, say now again, this is this U and the V axis are the horizons. And then if you look at the operator phi r in the right region at the location x1, and then you evolve it, and then you look at the commutator with another operator at x2 in the left region. So this x2 have a horizon. So if this right operator can force through the horizon and enter the light cone of this x2, then you expect this commutator to be non-zero. And indeed, you find that precisely this becomes non-zero when this S equal to U1. Yeah, U1 is negative because it's on the right region plus U2. And precisely is that this null distance from this point to reach the light cone, say, of the phi of x2. So even though the evolution is actually non-local, okay, so it's actually there's a finite spread, but spread in a way which is compatible with causality, with a sharp causality. Okay. Okay. So now actually there's a more surprise. So now if we
Elliot,
can
do you have a question, I think?
Yeah. Okay. Yes.
Just a quick question. So since you mentioned doing something like this in SYK, well, actually, never mind. That ignore the comment about SYK, but if these were fermionic operators, I guess this would become an anti-commutator and you'd have
Right.
the same statement.
Right. That's right. Yeah. Okay, good. Okay, great. So actually, you can actually do a little bit more. So if you look at this operator, this spark field corresponding to an operator with very large dimension. Yeah, by large dimension, I mean large order one, not proportional to n. So corresponding to a spark field with very large mass. And then you can actually then you can treat this this field using some kind of geometric optics approximation. So in that limit, you find that when you average over the spatial direction, say if you only concentrate on the time direction, and then you find actually this evolution become local in the bulk. And it evolves by transforming the initial Kruskal coordinate using the following way. A shift using the U Kruskal coordinate just by translation, but transform this V coordinate in a more complicated way. And so if I draw a plot, it behaves like this. Say if you just look at any operator in the left or in the right, then such kind of evolution, it generates its flow along this kind of trajectory like this. So if you are on the horizon, and then we'll shift along the u-axis, but otherwise, yeah. And it also preserves the boundary. So if the operators originally on the boundary is remains on the boundary. Okay. And this is the constant S slice. So if I start with the t equal to 0 slice in the bulk, and then the constant S slice when S go to a positive value flow like this, S go to negative value flow like this. Okay. So this is just one possible choice of U, right? As I mentioned, we can actually construct a different use, as I will make more explicit later. Okay, so to summarize the picture I want to advocate, so using the standard ADS-CFT story from the Killing symmetry of the right region and the right region and the left region, we can more or less do standard ADS-CFT to use the CFTR to describe the physics in the red region, to use CFTL to describe physics in the L region. And but if from the pure boundary point of view, that's what we know. Okay, and there are many, of course, indirect support by calculating various correlation functions, etc. And you know that these things are connected, and there's a future and past regions. But there's no direct construction of the future past region. Yeah. So what this US does for you is I start with this correspondence, okay, and you can actually construct the full black hole geometry. Okay, you can construct the full black hole geometry. And as I mentioned, so essentially this US leads to new emergent unfolding time. Okay, and I should also, yeah, I already mentioned there's actually infinite number of choices of such unfolding times. So this is consistent with our intuition because at the classical gravity level, the choice of time, there are many choice of time. You can do many different choice of Cauchy slices. But the surprising thing is that you can actually do infinite number of them intrinsically from the boundary point of view, which means from the bulk is by definition a diffeomorphism invariant. Okay, by definition diffeomorphism invariant. Okay, so now let me just explain a little bit the technique we used to do this. So this is by trying to understand the entanglement structure in relativistic QFT. So let's just consider, yeah, let me just first quickly recapitulate our standard story just for entanglement of a general quantum system. So if you have entanglement, say if you have a system, let's consider one separated into 1 and 2, they are complementary to each other. And then let's assume the Hilbert space can be factorized into H1, H2. And then by, say if you start with any state, you can also do density operator too. And start any state, you can trace out part of the, trace out one of the system, you get density operator, say reduced density operator for 1. And this row 1 contains all kinds of quantum information. Okay, and the quantum information science is about how to extract many different, say, observables from row 1. Random entropies, entanglement entropies, etc., activities, many different things you can do. So this S1 is just one, so this von Neumann entropy is just one example. Okay. But now if when 1 and 2 are highly entangled in the following sense, say if 1 and 2, if row 1 and row 2, you can simply define row 2. But now when row 1 and row 2 are both full rank, okay, when they are full rank, of course, you know that they must be highly entangled, because if they're not entangled, then row 1 and row 2 will be a pure state, okay? And when both row 1 and row 2 are full rank, and now it turns out there's additional structure, okay? The additional structure is that you can construct something called a modular operator using this way. You can define delta equal to row 2 times row 1 minus 1. Of course, to do row 1 minus 1, you require to be full rank. Otherwise, this inverse is not meaningful. Okay. And then using this delta raised to pure imaginary power, say to power IT. And when you act on the operator for either system 1 or system 2, so this BH1 denotes the operator, say bounded operator in H1 or bounded operator in H2. Okay, so this delta have the special property that I can actually, when you act on such flow, yeah, so this is a unitary evolution. To operate in the system 1, it remains in the system 1. If you act on the system in system 2, it remains in system 2. Of course, it's trivial in this example because row 1 and row 2, they're factorized. Row 2 and row 1, they commute with each other, and then this is trivially true. Okay, but this is only possible when they are full rank. Okay, and so this is normally called the modular flow. And the non-trivial thing about this modular flow is that instead of talking about them to be full rank or to be highly entangled, if we know that modular flow exists, okay? And that can be considered as a hallmark that these two systems are highly entangled, okay? And turned out, all these earlier constructions don't apply to quantum field theory, and only this last way applies to quantum field theory, okay? And so that's why this is very important for quantum field theory. So now let's go to quantum field theory. So now let's consider QFT in Minkowski spacetime. And now let's go to what Matt asked. So how about let's just consider two Rindler regions. Okay, let's just consider two Rindler regions. And yeah, you have Rindler right and the left regions, they're entangled, and then you have future and the past region of the Minkowski spacetime. And so it is often said that the Minkowski vacuum state, say if the QFT is in the Minkowski vacuum state, and then it can be interpreted as thermal field double state for the right and the left Rindler patches, okay? And so that's a way to see that these right and left systems, they're highly entangled with each other, okay? And indeed, this point of view is very powerful, has given us lots of remarkable information about quantum field theory. But here I want to emphasize a subtlety in this story. Say, strictly speaking, okay, if you rigorously speaking mathematically, the statement that this Minkowski vacuum is like a thermal field double state for the right and the left Rindler patches, this is only correct in the discretized theory. Okay, so you have to discretize the system, or you put some kind of hard wall, people call it the brick wall there at the Rindler horizon. And so normally this kind of difference between the discretized theory and the continuum limit, they don't matter. But in what I'm going to say, they actually play a fundamental difference. Okay, they play a fundamental role. So here I want to emphasize there are some fundamental differences between the discrete and the continuum cases. Okay. So let's just make a comparison between the discrete and the continuum cases. So in the discrete case, we have local Hilbert space. Say if you put the system on the lattice, and then we have local Hilbert space for the left region and the right region, and the full Hilbert space can be written as a tensor product of the right Hilbert space and left Hilbert space, just as our standard story I mentioned earlier. But in the continuum limit, actually such kind of factorization of Hilbert space don't exist. Okay, there's no local Hilbert space associated with the right and left region. Okay, and accordingly, so here you can define reduced density matrix. Accordingly, here there's no way you can define a reduced density matrix. So in the discrete case, then there's a finite von Neumann entropy and the Rayleigh entropies, etc., even though they depend on your cutoff. But it is something well defined in the discrete system. But in the continuum limit, of course, as is well known, this is not well defined. All the entropies become infinite. Okay. But so all these structure which are in the discrete system or for general quantum systems, they don't exist for quantum field theory. But the only thing remains is that the modular operator and the modular flows exist. And that's a quantum field theory way to tell us that actually the left and the right region are highly entangled. Okay. But there's also an important distinction between the discrete and the continuum in this case. So in the discrete case, as I wrote before, the modular operator can be written as rho 2 times rho 1 minus 1. So you have a factorized structure between system 2 and system 1. But in the continuum case, because you no longer have a reduced density matrix, such a modular operator actually mix the degrees of freedom in two systems, right and left degrees of freedom in a complicated way, so they cannot be factorized. Okay. And also, closely related to the above structure, even though at the superficial level it's not obviously related, is that in the discrete case, there's no sharp light call. Okay, so this is related to the Matt's question But in the continuum case, of course, we have sharp light cone. Okay, and similarly, we are with the later story with the black hole horizon, and that the black hole horizon can only emerges in the large n limit, in some kind of limit, and and all these differences between the discrete and the continuum case, okay, turns out they can be understood as the fact that the operator algebras in the Windler right region have very different structures for the discrete case and for the continuum case, okay? And this very different structure can be summarized in the mathematical language is that the operator algebra in the right region is a type 1 monomer algebra. Okay, the operator algebra in the continuum case in the right region is so-called type 3-1 monomer algebra. Okay, so earlier Vijay asked the question, what is type 3-1 monomer algebra? So unfortunately, I will not have time to give you a precise definition. And I would say the hallmark of the type 3-1 monomer algebra is using the simple mathematical term is that there's no finite projectors. Okay, so if you have a quantum system, say let's look at this type 1 case. Just say if you have the Hilbert space HR, okay, and now let's look at the operator algebra HR. Then of course you can construct, say, rank 1 projectors, which is just the pure state. Some pure state, you take the density operator of that pure state, and then that gives you the rank 1 projector. And the interesting thing, rank 1 projector is what we call the minimal projector. And the interesting about this type 3-1 monomer algebra is that there's no any finite rank projectors. Okay, any projector in this type 3-1 monomer algebra, they're infinite rank. Okay, they're infinite projectors, and that's essentially underlines all these properties I mentioned above. And
may I ask a quick question about that?
Yeah, just heuristically, let me just say one more sentence. Just heuristically, you can use the above feature I mentioned here to ask a heuristic way to understand this type 3-1 monomer algebra. Just type 3-1 monomer is the one which gives you those features. Okay, yes, Vijay.
So when you were talking about the discrete case, it sounded as though you were saying that a rank 1 projector is basically something associated with a pure state, because then you get something rank 1. So so in the continuum theory, there are pure states too. So why aren't they rank 1 projectors in some sense?
Good. Yeah, that's an important question. So in the continuum case, there's a rank 1 projector associated with the full Hilbert space, but not with the right region. So here we are looking at the operator algebra only in the Windler region. So that's the key.
Because the projector has to be in the algebra.
Right. And so the fact that you have this enormous amount of entanglement in the UV modes across the cut for the QFT makes it then impossible to construct anything that's localized on the right algebra. Is that right?
Heuristically, that's right. Yeah.
Oh yeah, I'm just asking heuristic, I guess. Yeah. Interesting. Okay.
Yeah. So
one way you could think about it is if you had these projectors on both sides, then you could act with them to get a product state, but there aren't any product states in the Hilbert space.
Sorry, that I didn't. So that I'm not understanding as much, because I can understand that the Hamiltonian produces states that entangle, because the kinetic term, if nothing else, will entangle everything in sight. But in the Hilbert space, I would have thought I could write down an ultra-local factorized state. I'm allowed.
Absolutely not. Well, I mean, this is a question of what you mean by quantum field theory.
Right, Vijay. For those states, they will have infinite energy.
Yeah, they'll have infinite. So the Hilbert space is defined as
Okay.
superpositions of finite energy states.
Okay, fair enough. So if you agree, so if you want to restrict the states of finite energy, which I guess you should or must, then those things don't exist. Okay.
Well, you allow limits, right? Like you allow normalizable states, which are sums of states of finite, energy going
Yeah. No, understood. So if you
That's
define
the world where the algebra is type 3. There is a world where the algebra is type 1, but it's a much bigger Hilbert space.
right, okay, so fair enough. So you set up your energy bound. You agree that you're going to look at states below that bound. You take sums, you take the limit, and you're allowed to include whatever appears in the limit, and that won't include such ultra-local states. Agreed.
Right.
Okay, interesting.
Yeah. Here actually there's a profound point, which is very different from our normal perspective. So you can think about it from our normal perspective. Say if you look at all finite energy states in your Hilbert space of your quantum field theory, and then you just find you cannot factorize them. If you write factorized states, they have infinite energy, etc. So this is one way to understand it. But another way, I think it's a more fundamental way to understand it, is that somehow, if you look at the operator algebra in the right region, you don't have to look at the global structure of your Hilbert space. Just only look at the operator algebra in the right region, some localized region, just to look at this local operator algebra. If I find it's type 3, 1, then I can already tell you, in your Hilbert space, there's no such states, okay? And the algebra structure actually determines the structure of your Hilbert space, okay? I think that's a profound fact, which is not normally emphasized. Yeah.
I'll be on as a question.
Good. Yeah.
So I might have missed something basic here. I mean, I understand these statements say in Riddler space in Minkowski, but you're at some point also talking about ADS. With two-sided ADS, you can certainly factorize. You can certainly write down states which are factorized between the two sides. So
You mean the gravity side?
yeah,
No, you cannot. Actually, yeah.
well, just as CFTs. I mean, I could just write down a tensor product of two CFTs, or the
Good.
is it or the
Good.
entangled state?
Yeah. I mean, that's a question I will comment on. It is the key. Yeah, it's one of the key of the key point which will emerge in this talk. Yeah.
Okay, I'll wait till you talk about it.
Yeah.
Hong, can I? Yeah. So is there some at least intuitive sense in which your right column can be considered as a limit of things in your left column? I mean, I realize that trying to do that rigorously mathematically might be very, very hard, but is that even heuristically correct or not?
I think in principle they can, but I don't think we understand this limit very well. Yeah, in principle, but I don't think we actually understand this limit well.
I mean, we would like to think that when we discretize a QFT, obviously we're making an approximation. It's not the same as the continuum one, but then hopefully we can recover everything we would want to know about the continuum by taking the continuum limit.
Right.
And you think that's not true?
No, I'm not saying it's not true. I think it may be possible to do this way. It just mathematically is non-trivial. So mathematically, one can construct, say, this type 1 or type 3-1 monomer algebra using a limit, say, of the type 1 monomer algebra. You can construct such a limit, and those limits which mathematicians have constructed, to apply them directly to this Rindler case, the discretized Rindler case, is not straightforward. I'm just saying. Yeah.
I mean, in free field theory, though, I think we understand it pretty well, actually, right? Like, for example, you can start with the Rindler vacuum on the, in the Rindler eigenstates on the two sides, right? And take the tensor product, and that gives you a Hilbert space that factorizes, but it's much too big. And then you do this thing where you restrict to, you know what the states of finite energy look like in that Hilbert space, right? And then you can construct the algebra of smeared operators that preserves that live in the region and act within the low, the finite energy Hilbert space.
Well, that's not quite a limit of a discrete theory, though.
Well, yeah, you can further discretize the Rindler wedges, I guess, if you want to. That's right. Put in a lattice or something. Yeah.
Yeah. I'm just saying the limits. should exist. You should be able to do it, but to do it rigorous mathematically, I don't think there's explicit construction at all.
Okay, but it is something reasonable to kind of have in your head, to have the idea of it.
Yeah.
Okay.
Yeah, absolutely.
A quick follow-up. So we, of course, believe that the UV completion of the quantum field theories is via string theory and might legitimately expect some sort of softer behavior in the entanglement structure, UV entanglement structure in the string theory. So here we're talking really about algebras defining quantum field theory. Is there any way of meaningfully thinking about that? Obviously, it's very challenging to think about that in string theory or in string field theory, but any thoughts on that?
Yeah, good. I mean, it's a very important question. I will mention maybe something on this later in the discussion part. I think maybe we can come back to this question. Yeah.
Okay.
Matt, do you have more questions?
No, sorry.
Okay, good. Okay, great. So so the story is actually general for relativistic CFTs, QFTs. So for any local region, and the local operator algebra can be associated with the type 3-1 monomer algebra. And the entanglement for any local region can be understood in terms of modular flows, so associated with such algebraic structure. Okay. So in the sense, this type 1 structure, type 3-1 structure plays a fundamental role in understand the entanglement of a continuum quantum field theory. But here there's additional surprise. So this type 3-1 monomer algebra actually give you additional structure, and this additional structure then give you the tools for for emergent times, which are not available for other kind of algebras. Okay. So now let me tell about these tools which are unique to type 3-1 monomer algebra. So unfortunately, I have to use a little bit mathematical language, but this language I can translate into language you're familiar with. So we say, suppose M is a von Neumann algebra, and the vector omega is cyclic separating for M. Okay. So the M. So here, just imagine the M is the operator algebra in the right Windler region. Okay. As I mentioned, it's a von Neumann algebra. And this vector considered to be the Minkowski vacuum of the QFT, and that this vacuum is cyclic and separating for M, which is the algebraic language, which is a continuum language. Say what I said earlier about the discrete system is that I said that both row 1 and its complement row 2, they are full rank. Okay. So when both row 1 and row 2 are full rank, when you express in terms of algebraic language, that is called cyclic and separating. Okay, I will not go into detail there. It's not important. Anyway, just say, but this notion applies for the case which cannot talk about reduced density matrix. Okay. So now it's this monomer algebra, and then as I mentioned, there's modular flow. Okay, and now let's suppose there exists a lot of monomer algebra, sub-algebra of M. Okay, so you can consider, say, the right Windler region and then a sub-region of that. And now suppose this sub-algebra have the following properties. It said this is cyclic for N. Again, this is this is some technical property. Don't worry about. Just this N has to be chosen properly. Okay, properly. And then, but here's one important thing about M. It said now if you flow using the modular flow of M, okay, as I mentioned for this monomer algebra, you can have a modular flow. If you use the modular flow of M to act on these operators in N, the sub-algebra, it still take you within the sub-algebra M for half-sided of the evolution. Okay, it's only for t greater, smaller than 0. For t greater than 0, it can be take you outside N. Okay, but say for t smaller than 0 belongs to N, and then we call this is the we call this structure half-sided modular inclusion. Okay. So when this is when you have such a sub-algebra N and M and the original algebra M, yeah, and then you have this modular flow structure, and then can be shown, okay, powerful mathematical theorem in early 90s by Borchers and Westbrook. They can show that for type 3-1 algebra, then actually there exists a unitary group US with the following properties. Okay, this US can be written as some generator of G, and this G is bounded from below. Okay, and this G actually leave your vacuum invariant. This US, leave your vacuum invariant. So the vacuum is actually symmetry under this flow. Okay, so now from what I mentioned earlier, you have an operator, Hermitian operator, which is bounded from below, and then this is the candidate of a new time. Okay, so if you find such kind of sub-algebras, and then you have emergent new time. Okay, and so that's what we are going to use. Okay. Okay, so now let me give you a simple example just to give you some intuition. So let's again consider this Windler region, just one plus one dimensional Minkowski space-time. So let's take M to be the operator algebra in the right region, which are shaded by this orange color. Do you call this orange or you call it pink? Actually, I don't. Yeah, anyway, this color, this all full right region. And now suppose now I take this sub-algebra N to be a region in this purple region. Okay. And then as I mentioned, if you have the original von Neumann algebra, you choose a sub-algebra, and then you can show that this N actually satisfies these modular inclusion properties, and then that leads to a non-trivial emergent G. Okay. It turns out here G is something we understand. Turns out G just generate the translation along the x minus direction. Okay, essentially just generate along the x minus direction. And if you choose some other sub-algebra N, then you can actually generate translation in the x plus directions. Okay, and you can consider more, compositions of them, etc. So the bottom line is that this U, when you act on M, for s smaller than 0, it takes you within M. So if you act operators in the right Windler region, it takes you within the right Windler region itself. But if you act on M, of course, if you have a null translation along x minus direction, then in particular, this sub-algebra is just take, say, in some normalization, just -1, then take M to N. Okay. But now if you take s greater than 0, and then can take you beyond this right Windler region and take you into this F region of the Minkowski spacetime. So in this way, when you act this US on the right and the right and the left Windler regions, actually can be used to generate the future and the past regions from the algebras of the Windler and the right regions. Okay. So to say another way, starting with the Windler time in right and L, we actually obtain the Minkowski's time. Okay. So now this will ring a bell. Okay. So that's what we want to push to the black hole case. There we want to start with the Schwarzschild time, which we know as the non-boundary time, and we want to generate the Kruskal time. Yeah, because Kruskal time is like Minkowski's time when you make the analog with the Windler case. Okay. And so essentially this is the idea. Okay, this is the idea. Good. So the key is that if, when you identify this type 3 von Neumann algebra and appropriate chosen sub-algebra, that can lead to new emergent times. Even though in this particular case, it's not really new because the null translation we do know for Minkowski space-time, but at least that's something you can do to generate from the Windler time. Okay. Yes, Veronica. Yeah.
Just to make sure, if you discretize the space-time, you could have said everything you said in some sense on this discrete structure, even for type 1, right? You could have generated some operator that got you out of some subset of them, right?
Good, but then this actually, so if you do it in a discretized case, even though such kind of discrete, say this kind of law translation, of course, still is there. Depending on how you do your lattice. And but it can no longer be generated out of the Windler time. So the key is only in the continuum case you can generate this Minkowski space, Minkowski time, or this kind of law time from the Rindler time.
I see. So even if you try to do, so yeah, I think I'm still not fully appreciating why is that continuum structure.
Yeah, right. Yeah, there's a mathematical theorem to prove that this structure only exists for type 3.1. It just does not exist for type 1. You cannot do. You cannot have the properties which we want, including G is bound. For example, you may have. For example, G will not bounded from below, etc. Yeah, just if you want to satisfy all these properties, and it's just not possible for type 1. That can be proved mathematically.
May I ask a question about that?
Yeah.
In the earlier sort of qualitative discussion of why these things obtained and why 3.1 was different and so on, the observation was made that one of the key things that happens is the enormous amount of entanglement stored in the UV modes in a continuum theory across the cut, and that sort of changes the structure of the problem. So suppose I had some discrete system of the kind that Veronica was talking about, and is the problem in terms of getting this construction to get the sort of the inside region that you can't make enough entanglement between the two wedges? Is that the problem, or?
Good. I think heuristically, Vijay, I think that heuristically you can understand that way, because if you have a type 1 structure, then you have a factorization of the Hilbert space. And then in that sense, the amount of entanglement is already limited by your structure of your Hilbert space.
In that case, can I ask a question whether one could sort of push that as a way of probing the idea a little bit more?
Yeah, 1 second.
If one could do the following thing. So suppose I agree that each of the sites of this lattice in this type 1 thing had some n by n matrix. And I let n get very large, so I'm getting huge numbers of degrees of freedom. And then those I can entangle, to produce very large quantities of entanglement in the left and right. And then I could imagine some kind of paired limit where I take n to infinity while doing whatever else.
Perfect, Vijay. That is our black hole example. Our black hole is like that.
Oh, I should have read your paper.
Yeah, our internal black hole is like that because we have safety right and we have safety L. And then there's a large n there. And indeed, you will see there's an emergent type 3 structure when we take n go to infinity limit.
Okay, thanks.
Yeah. Good. So yeah, anyway, so this is the take-home message that what this type 1 3.1 algebra can do for you is that it can actually give you a new emergent time. Now let me just describe this boundary construction of emergent importing times. So first I have to explain there's actually an emergent type 3.1 structure in this thermosphere double story. So the black hole is described by CFT-R times CFT-L in the thermosphere double states. And now we can consider the operator algebra in this theory. So for technical simplicity, let's consider bounded operator algebra of CFT or CFT-L, they're type 1. Okay. Because they have Hilbert space, there's a tensor product of Hilbert space here. And so any operators acting on the Hilbert, any full set operator on the Hilbert space, it's a trivially type 1 von Neumann algebra. Okay. But now we want to argue, as Vijay was actually asking, actually there is actually emergent type 3.1 von Neumann algebra in the large n limit, which leads to the emergent, and this emergent type 1 von Neumann algebra then leads to importing times and emergence of sharp horizon material. Okay, so now let me explain where this emergent structure comes from. Now let's look at the algebra generated by single trace operators in the CFT. Okay, say this you can do it for both left and right. Let's say look at the algebra of operators, single trace operator in the CFT-R. So of course, this single trace operator also acting on the Hilbert space of CFT-R. When you act on this Hilbert space, actually, due to some technical reason I will not explain here, this AR, this single trace operator algebra is actually not the von Neumann algebra. So we don't even talk about whether it's type 1 or type 3. It's just not it's not even a monomer algebra. But now it turns out there's another Hilbert space here in the Nagier limit. So in the Nagier limit, actually there's another Hilbert space, which I call HGNS. And this is a Hilbert space of small excitations around the thermal field double states. Okay. So by small excitations, we mean you can act or finite number of single trace operators on the thermal field double states. And so you can show mathematically rigorously, okay, that actually that forms a Hilbert space. So that's why I call it HGNS. Even heuristically, it's very simple. If you want to do it mathematically rigorously, you have to use so-called the GNS construction. Yeah, anyway, heuristically, it's very simple. There's a Hilbert space of small excitations around thermal field double states. And now you can look at how the single trace operator algebra acting on this Hilbert space, which is only possible in the Nagier limit. Okay, you can define this Hilbert space precisely only in the Nagier limit. And then now let's call the algebra of this AR in this new Hilbert space to be MR. Okay, so MR is essentially just a representation of your original single trace operator algebra in this.
What do you mean by small in this case? Is it small and average energy or?
Yeah, just take thermal field double states. Just like you, by small just means that you act on single trace operator with, say, dimension of order 1, but you only act on number of them which is independent of n.
Okay.
Yeah. Yeah, then you can show actually it forms a Hilbert space structure. Good. Vijay, you have other questions? Okay. Good. So now let me call this algebra MR, which is the algebra of this AR in the single trace operator algebra in this GNS Hilbert space. Now the conjecture. Now you can also do similar thing in the left. Okay, in the left. The conjecture is that this MR and F flat are type 3-1 algebra. And in particular, just related to Alvin, you were asking earlier, even though the full Hilbert space have this factorized structure, say for CFT-R and CFT left, but this GNS Hilbert space does not factorize. And that's, in some sense, is also dictated by this type 3-1 structure here. And this non-factorization actually is related to non-factorization in the Bach. Okay, in the Bach, you cannot factorize. Yeah. Good. So there's some supporting argument for this. I don't have a precise mathematical proof. And first, you can look at spectral functions of single trace operators. You can also show that actually we can construct explicitly this half-sided modular inclusion translation structure for such algebras, which then show, yeah, which can be considered as a self-consistent evidence. Okay. And then the duality with the Bach. Okay, so now let me just comment on this last aspect because I think people can understand it easily. So in the Bach, let's try to understand the algebraic structure in the Bach. So in the Bach, so let's just consider small excitations, again, small excitations around the black hole geometry. So there we can construct the Fock space around the black hole with the Hartle-Hawking vacuum, okay? And then we can call the operator algebras, say, of the gravity field on the right, in the right region to be M tilde R, and in the left region of the black hole to be M tilde L. Okay, so this is all can be formulated in perturbation theory in G Newton as quantum field theory in the curved space time. Okay, and then our standard duality for the internal black hole in particular, now people call the local, for outside the horizon, sometimes people also call the sub-region duality, say applied to the outer horizon, is that this GNS Hilbert space is actually should be identified with the Fock space of the black hole. And this GNS vacuum, which is essentially the Sommerfeld double state itself, and should be identified with the Hawking vacuum. And then their corresponding operator algebra should be identified. Okay, so this is just a standard story. The single trace operator algebra should be identified with the operator algebra in the block. So we have the single trace operator algebra in the boundary, and the operator algebra in the block, in the right region, etc. Okay, so this identification just is standard part of the standard ADS-CFT dictionary, but just now we are expressing it in terms of algebraic language. And so now the key is that since in the block we are talking about quantum field theory in the curved space-time, so from just the general result of quantum field theory, and this M tilde R and M tilde R should be type 1 modular algebras. In particular, in the block, there should not be factorization between the right region and the left region. Okay, yeah. And so that also implies that this MR and ML should be type 3. Okay, so now we know that we have this emergent type 3-1 algebra in the boundary, which only appears in the Nigerian limit. Then we can try to find this US. Okay, and we just find some appropriate von Neumann algebra of MR. Okay, so to do this, let me just mention some general remark. So where the theorems of these half-sided modular translations are very powerful, they ensure the existence of such kind of emergent time. But finding it explicitly in general is very, very difficult. Okay? Even for free series, not easy. And so here in the Nigerian limit, the algebra of single trace operators in the GNS Hilbert space can be described by that of generalized free field theory. Okay, turns out in this case for generalized field theory for the full space time, actually the expression of this US have a universal form. You can actually, actually in this case you can actually construct it explicitly, just using this generalized free field structure. Okay, and so this expression of this evolution have a universal form up to a choice of phase factor. And the explicit structure of the algebra itself, the details of the algebra itself, is only encoded in this phase factor. So everything else is universal. Okay. And is universal. Okay. So that will enable us to construct such kind of US explicitly. Okay, so before I tell you how do we construct such a sub-algebra, let me just make a general remark. So if you consider causal diamond in the space-time, in the quantum field theory. So look at the operator algebra associated with this Cauchy slice A1 and the Cauchy slice A2. Say if you look at the operator algebra associated with these two slices. So in the general quantum field theory, they're just equivalent, they're the same algebra. It's because A2 can be expressed as the evolution of A1, okay, just from the standard Heisenberg evolution. But the key for us, this is not so for algebra of single trace operators. So if we look at the algebra of single trace operators, which is what we are interested in right now, A1 and A2, they're inequivalent. Single trace operator defined on A1 and single trace operator defined on A2, they're inequivalent. It's because when you evolve the single trace operates on A1 using Heisenberg evolution, that take you outside the algebra of single trace operators. Okay. So if you restrict to the single trace operator algebra, they're actually not equivalent. So this is a very important point because this gives us enormous opportunities for constructing new nice sub-algebras. Okay. So now I can just find get emergent boundary times just by constructing some nice sub-algebras. For example, let's consider, let's think this full rectangular is the full space-time. Okay, the vertical direction is time direction. So suppose this is 1 + 1 dimensional space-time. Say if this is on the circle, then you can imagine the left boundary and right boundary are identified. And so this is the full space 1 + 1 dimensional boundary space-time. And we can consider the M single trace operator algebra to be the algebra defined on the full space-time. And then a sub-algebra will be a algebra defined on the half space-time, say up until say t equal to 0. Okay, that only runs t equal to minus infinity. And so if you have an ordinary quantum, if you consider the full operator algebra, then this n and m, they're equivalent because they just evolve by single Cauchy slice. Okay, but again, I emphasize because they're single trace operator algebra, these two are not equivalent. Oh, Elliot, you have a question?
Yeah, I think I'm just misunderstanding something, but
Okay.
the trace of an operator is preserved under unitary evolution. So what do you mean by single trace operator?
Oh, right. Yeah. This is a technical term. So this is a technical term for we consider this kind of gauge gravity. This ADS-CFT duality. For example, suppose the boundary series is given by a Yang-Mills series, and in the Yang-Mills series there's some gauge group SUN, and then you can write down say the operator like F squared, say F mu mu, F mu mu. But in order for this to be gauge invariant, you have to take a trace for the long abelian series. And the operator which contain only a single trace, we call single trace operator. Does this make sense?
It's not a trace in the Hilbert space. It's a
It's not
trace.
trace in the operator. It's a trace in the definition of the operator in the gauge group.
Okay, thank you.
Yeah, in the gauge group. Yeah. Good. Okay. So this gives you a sub-algebra, and potentially this can give you a new emergent time. You can consider other sub-algebra, consider n to be just the future part of the space-time after some time. Okay. We can also consider the sub-algebra which is not a constant t slice, which covers this region. And we can also consider sub-algebra which cover that region, which again, this is curved in space. Okay, some non-trivial curve in space. So in principle, you can construct infinite number of such kind of sub-algebras and the infinite number of emergent times. Okay, so now let's look at this simple example. Okay, so this is a full space-time algebra, single trace operator algebra, and then you look at the sub-algebra which only up to t equal to 0. Okay. But even though we can determine, even though in the large N limit, we can determine the structure of this US up to over a phase, but finding that phase is actually a strongly coupled problem. So if you want to do it for equal to super Yang-Mills series, okay, or to do the CFT dual to the ADS3. So this is actually a strongly coupled problem. So we but here we can get some help with the duality. So we conjecture that this operator algebra in N, okay, which is cover full space, but only up to t equal to 0. This is dual to the operator structure, operator algebra in the black hole space-time, corresponding to this causal wedge of N in the black hole space-time. So essentially covers this region in the black hole space-time. Okay, so we conjecture, yeah, we have some support for it. I will not go into there. Anyway, just say we propose that this operator algebra in N tilde and N, they actually can be identified. By this identification, then we can actually calculate this phase using the gravity calculation, because gravity is just a genuine free field series. Anyway, so we can calculate it in the gravity side. Then you find actually this phase factor is actually given by the phase shift at the horizon. Okay, so if you're familiar with, say, the wave function, say, of a field, of a Bach field in the black hole geometry, and you know that the any Bach field in the black hole geometry, when you go to the horizon, reduces to a superposition of plane waves, and there's a phase shift between the ingoing wave and outgoing wave, and it turns out it's precisely that phase shift which give you this phase shift, which give you this phase factor in this emergent time evolution. Okay, so if you do that just for this choice of N, then you get this kind of Kruskal type of U flow I mentioned earlier. Okay, so along the horizon, you just flow along the U axis. And if you now you can also, if you choose n to be like this, and then you can, and then we get we conjecture it's due to the region like that, and then it will lead to the flow which the horizon is like V translation, and again will lead to some flow like this. And you can also look at infinite others, say, and you can also consider compositions of such Kruskal U and the V type of flows. When you compose them, and then the flow on the horizon is no longer log, in principle be time-like. Okay, like in principle be time-like. So in principle, even though we didn't do explicitly, I expect to be very complicated. In principle, you can imagine by some complicated choice of the shape of n, and by certain compositions of them, we may actually be able to construct a genuine Kruskal time. Okay. So now let me just mention some quick generalizations. Oh, I didn't realize it's so late. Okay, let me just make a few quick remarks. So first, this emergent type 3 is actually ubiquitous. Okay, so let's just consider, earlier I was talking about some of your double state. Now let's just consider boundary CFT in the vacuum state, and just consider some local region R. Okay, and then the full operator algebra in R is type 3(1). As I mentioned earlier, for quantum field theory in the local region, the operator algebra is always 3(1). But it turns out even in this case, there's a lot of emergent type 3(1). So now if we look at the completion of single trace operators, single trace operator algebra in the region R, and then you can argue that's actually emergent type 3(1) algebra in the large n limit. Okay, so actually associated with the region R, there's two now type 3(1) algebra. One is the one for the original theory, and now there's an emergent one for the single trace operators. And they actually reflect differently in the bulk. So these two type 3(1) algebra actually leads to two different types of divergences in the holographic entanglement entropy. Say suppose this is the boundary, and this is the bulk. This is the inside circle is the bulk, and then this is the boundary region R, and this is the Euler-Hagelage surface. Yeah, because we are let's look at the constant T slice. And then the type 1 algebra, type 3(1) associated with the full operator algebra is related to this RT surface, is infrared divergent near the boundary. And this emergent type 3(1) of single trace ordered algebra is related to the divergence of the entanglement entropy in the region of this entanglement wedge across the RT surface. Okay. So that's the divergence which is related to this type 3(1). And anyway, let me just skip here. You can also prove some kind of no-go theorem that with very simple requirement, say require that this flow, for whatever kind of flow, take you behind the horizon. Just forget about our earlier discussion. Just imagine abstractly we want to construct some boundary operator beyond to generate flow behind the horizon, but it's bounded from below, then you can show that this is only possible in the you can show that this is a sharp horizon is not possible at finite end. Because at finite end, at most you can get this type 1 monument algebra, and that will not give you a sharp horizon. So this is very similar to the situation in the discretized QFT. So when you discretize the system, then your sharp light cone is gone. Okay, only the sharp light cone only counts when you go to the continuum limit. Okay, so I think I can actually stop here, and if people, good, because it's very late. Yeah.